started. So today we're going to pick up from where we left off last class. We left off just having done some math involving page tables, figuring out how many frames we have, how many pages we have, based on the split up of bits in that address. We're going to get a couple practice problems later on that, so please look forward to it. So today we're going to start off talking about fragmentation and then some issues involving pages. So to get us started, the first question here is, does paging prevent internal fragmentation? So we see that it prevents external fragmentation because now, instead of having this setup that we had before where we sort of have blocks of memory allocated to a contiguous region allocated to a process and trying to sort of fit the processes into these holes as best as possible, now we can allocate pages to any process that needs it. So if we have a process requesting memory, we just take 4 kilobytes or whatever our page size is and give it to that process. So we don't have any external fragmentation because we can divide our memory up into page-sized blocks. We can end up in a situation where we just run out of memory and we can't allocate to a process, but we can always do things like swap that process to disk or swap some pages to disk and then free up space in physical memory for a process. So we can completely eliminate any of the external fragmentation that might occur. So the first question is, and we'll just do this one sort of quickly, you don't have to move to rooms for this, do we prevent internal fragmentation with paging or not?
No.
No. Okay, so why not?
Because if you had a process that needed like half a page, you still have to like give it a full page, and then you just kind of like still have that wasted half a page.
Correct, yeah. So because of the fact that we are allocating in these like 4 kilobyte blocks, it is definitely possible that a process only wants half a page of memory, and we're just going to give it a whole page because that's our sort of allocation granularity. That makes it a lot more reasonable to manage this amount of memory that we're trying to keep track of by sizing things in pages. So we don't end up preventing internal fragmentation, but that's fine because usually, we can, assign reasonable values to our pages. We have to basically determine our page size to make sure that we are minimizing internal fragmentation while trying to also minimize these storage requirements for things like the page table. So we saw before, if we have a 4 kilobyte page in a 64-bit system, there are 2 to the 52 pages that we have to keep track of. And we will get to this in another class. I think the next time we meet, Friday, we'll talk about some formats for page tables that make them feasible to fit in memory when we have possibly 2 to the 52 pages to keep track of. Or even in the case that we were using 48-bit addresses, we would still have 2 to the 36 pages to keep track of, which is still way too many to keep track of. So in some cases, or when a page is not already in physical memory, the hardware will trigger what's called a page fault exception that will cause that page to be loaded into physical memory. So this is in the case that we do have the external fragmentation, not external fragmentation, but we have more memory requested than we can physically keep in memory. So we have a lot of processes running. They're all requesting memory. We sometimes have to put things back into disk, unload them from physical memory, and replace it with someone that's currently running. So that is a page fault. So when we try to access memory that we don't currently have in memory, we trigger a page fault. If that page fault is to memory that hasn't been allocated to a process, that causes a seg fault, meaning that we tried to access memory that was not already allocated. It's outside of the bounds of what the programmer has requested and been given. And these page faults can be a little bit expensive because we are loading memory into physical memory. We're essentially copying 4 kilobytes of stuff from somewhere, whether that is from disk or we're initializing it for the first time. We're doing something to 4 kilobytes of stuff in physical memory, which can be expensive. So I wanted to show you real quick how we can see the page fault statistics for a program. So here I'm going to run the command user bin time. So time is usually a utility that if we don't give it any options, and this is not a great command to run because it's going to show a bunch of stuff. But at the bottom here, we can see some time statistics here that show us how much time was spent on this process. It shows us how much user time, how much system time, and how much wall time was elapsed as that process ran, how much CPU usage there was during that event. And then it does have some stuff at the bottom here about page faults. We can actually get a slightly nicer view of this if we use the -v command, which is verbose. So it lines it up a little nicer for us, tells us what everything was there. So a couple things to sort of highlight for you. So user time versus system time. This shows you things like, was it waiting to be scheduled for a lot of time? We can see if a process was just sort of like sitting in the wait queue, ending up sleeping a lot more than we expected, things like this. Percent of CPU that this job got, we can see again how much time was being allocated to other processes. And then the wall clock time is like what you would get if you sat there and timed it with your stopwatch for how long it actually took to run. Now this was super fast, so given that this didn't even take a second, it doesn't really show anything here. But usually we can run a command and get a little bit more information about what's going on in terms of, is it getting stuck waiting for system calls to complete or waiting for the OS to do something else rather than actually running itself. And then I'm going to bring your attention to at the bottom here. There's a thing that says page size. So we can find out from this command what the system we're running on, what page size it's using. So 4096 bytes is 4 kilobytes. And that's what we're using on this system. And then we can see things like voluntary context switches, involuntary context switches. So these are the scheduling events that we've talked about before, how many times it's getting swapped out of the core for something else to run, either by its own request or by someone else's. And then we have here major and minor page faults. So these are the events that we're talking about right now that we don't have a page in memory and we want to put it in memory. So minor page faults, which you can see it has 133 of here, are when we don't have that page in memory yet. We need to allocate a new page. So we see a lot more of these because as this program executes, it requests some extra pages. It has to load things into memory. It has to read things from disk. But it's not actually like the major page fault would be the sort of more expensive one where we've stored something to disk because we ran out of memory space in physical RAM, and we have to load something back from the disk into that physical RAM. So minor page faults are not as expensive just because usually this is more initialization work than anything. But it can sometimes be important to check on this if you're running something that's using a lot of memory because the page faults can be expensive if we're loading things from disk, or if they are major page faults, or if there are just a lot of minor page faults because we're sort of constantly churning through memory and having to switch which things we are using in that loaded memory. So just sort of a useful command for you to keep in your back pocket, that this user bin time can tell you a lot about processes that are executing. There is another time command on the Linux system, and this is unfortunately not the same one that will show up if you run time. So if you just run time without the /user/bin/time prefix on it, it'll give you a different command, and it's not going to give quite the same output. So this is a small piece of what you get from user bin time. Just gives you the real user and system time that we see. So there's just the wall clock time, the user and system time that we would get from user bin time as well. But I usually prefer using user bin time to get information about running processes, because or processes that you want to run, because it gives you a little more detailed view of what this is actually doing. So it can be really helpful for like system debugging to figure out what's going on with an application. Any questions so far? Okay, cool. So in the case that we have a lot of page faults happening, you can use what are called huge pages to optimize a system that experiences too many page faults. These tend to be much larger than the normal pages. And they can basically say that, once we have this in memory, we don't have to worry about page faults because we've loaded this huge chunk of memory instead of the 4 kilobytes. So if I'm accessing, I know my program's going to access 1 megabyte of data. And I need to make sure that those accesses happen as fast as possible once the system is up and running. I may want to prefer to use that 1 megabyte huge page rather than 4 kilobytes because 4 kilobytes is going to have to do a bunch of loads in order to get all that memory. We're going to have a bunch of page faults, and if we know we're using some huge page sized amount of data, we can have a single page fault where we would have had hundreds of them instead with regular page sizes. So again, just want to go back here and show you how this works on a Linux system. So if we cat proc mem info, we can see at the bottom here there's some information about huge pages on our system. So we have the total number of huge pages, total number of free huge pages, the number reserved, so currently in use by processes, and I'm not sure what this last number is here. We can see the huge page sizes that we have. So in this case, on this system, the huge page size, the only one available is 2048 kilobytes, which is 2 megabytes. So this system can allow us to map 2 megabyte huge pages. It currently does not have any supported, so you actually have to do a little bit of work to enable huge pages usually because not every application wants them. And once we reserve space for huge pages, we can't use it for other stuff because we do have to indicate to the frames that we are going to use a huge page in that frame in physical memory. So we do have to change some parameters and basically let the operating system reconfigure things to reserve space for these huge pages if we want to use them. But right now we don't actually have any available to use. But if we did, we could use up to 2 megabytes per huge page. So again, this is a cat/proc/meminfo, just part of the proc file system that describes what our parameters are on Linux. I'm not sure how to use huge pages in Windows. I can look that up if anyone's interested, but I know I've only really used this in Linux to optimize things previously. So hopefully that's helpful. So next up, just wanted to sort of have you chat about very briefly what the advantages of using paging are as an abstraction for the programmer. So how does paging benefit you? Basically, what are we getting out of having this paging system as a programmer? Like, it clearly helps the OS because we don't have external fragmentation, but how does it help you as a programmer? So go ahead and split into rooms and discuss for like a minute or two and then come back. Thanks.
Does it help the user because then you're not having to keep track of necessarily you're not having to keep track of the physical addresses as much, like the OS takes care of that?
Shit.
I don't know.
That's what we got so far.
It gives you more freedom.
It gives you more freedom. How?
Depends.
It depends.
Yeah, that's a good answer.
Not really sure. I guess they're just like pages. Like I was saying earlier, like I guess you don't have to take into account like trying to fit in that specific amount of memory, because then you can just worry. You have the pages to work with, so as long as you're within that space. I don't know.
I think we're a little confused as to what, like, I feel like I feel like it might be helpful to like see like a visual of like how paging works. I don't know.
Okay.
Yeah.
So I guess we're comparing paging where we sort of have this allocation of, 4 kilobytes at a time to a process,
Right.
versus the contiguous memory allocation where you sort of say up front, this is how much memory I need, and you request that from the OS, and that it fits you into a hole in memory somewhere, and that's all you have at that point.
Right. So I think I understand, I guess, the difference.
So give you like, does it give you like a buffer? Like if your process goes over what you think it needs, it has like the rest of the page to use as well.
Yeah. So I mean, once you request a page, right? But theoretically, with this mapping system we have, where we have the process ID plus page number goes to a frame number. That means that you can use all of the address space as a process. So you don't actually have to, know how much memory you're going to use. You don't have to request it up front. You just keep using memory, and the OS will keep allocating the pages as needed for your application.
So it'll give you more pages if you need it, like for each process.
Yeah.
Okay. I guess that makes sense. And so then you'll be able to like navigate within those pages based on what number was it?
So you have your page number to frame number mapping. So like each process has their own page number to frame number mapping. So it doesn't have to necessarily fit into a specific amount of memory. It's just all of the memory is available to every process, essentially. Maybe that was a confusing statement. So I think the sort of what we're trying to get at here is that like as a programmer, you don't have to think about what memory you're using. So the OS and the hardware sort of handle that for you by having paging enabled. That you can just use whatever memory you want to use. You do still have to go through like system calls to request that the OS like set up that memory for you and be aware that you're going to use it. But that's just malloc and free and new and delete, that same sort of stuff you usually use anyways, or in a managed language like Python where you just kind of create variables and it handles it under the covers.
So is that how you like make sure that you're not overwriting memory from like another process? It's like
it makes sure that you're not using memory that you're not supposed to use yet, so that like if you went out of bounds of the memory that you expected to use, then it'll catch that. But, ideally, this is all isolated at this point. So you could write to memory that you're not supposed to write to, and another process won't be there because they won't have the same frame number as the page number to frame number mapping that you have.
Okay.
Cool. So I'm going to go to the next room. You guys can chat about it for a little bit more.
I don't know about that anymore.
Everyone, what do we got?
Okay. We were saying, I think the biggest thing is that it makes memory allocation easier for programmers.
Okay, so how's that? How's it easier?
So like you're not stuck trying to find like a hole or whatever that is gonna fit for whatever you need to do. You can just like ask for however much you need, and then like it'll just get however many pages you need to fit that space.
Right.
Do whatever you want.
Yeah, I think that's a good point, for sure. Okay, I'm going to move on, and then we'll come back to the center here. Oh,
That's good.
or is everyone in middle row now?
Everyone-
Am I
Everyone's in
supposed to be
middle.
here?
I'll put Beck in middle row now since we just migrated.
There's not enough seats in the middle row.
Yeah, we're all squished
You're
together
supposed
now.
to be like us. We're the best row.
Yeah, please maintain a 6-foot distance from everyone else in the middle row.
We're best friends. We should be close.
Okay, so what do we have in the front row? What was your answer?
We were kind of stuck. I was thinking though, since we're assigning like entire pages, if we're like trying to allocate a lot of memory, we could potentially like be wasting memory space for stuff that's not allocated while we continue to acquire new pages.
Okay. Yes, I think that's reasonable. And yeah, maybe we need I think someone was asking for a diagram, so let me see if I can I'll go live again and then see if I can diagram this quickly here. So I think the main advantage is like in the contiguous system view, right? We have this setup where like each address is, you know, mapped to some process, and this is each physical memory address is mapped to some process. So, you know, as a process, if you're this top one in the blue here, at the very top at the lowest address, that is your memory region. If you access outside of that memory region, that's another process's memory, and that you're sort of in the same your virtual address space or your logical address space is sort of cut off at that blue region. So you can only access from like 0 up to whatever your maximum address is, and you can't access beyond that space. Whereas in a page system, we sort of have this setup where, you know, we have, you know, the blue process maybe. So we have a blue process. It thinks that its memory space is the entire memory space. So we have process 1. Sorry, this is a little hard to do live. So we have process 1 that thinks it has the entire memory space in the system. And we can have another process, you know, process 2, that thinks it has the entire memory space in this system. So the sort of point being that every process thinks it has all of memory. I will make that one red. And then the actual main memory, or the actual physical memory, is going to be divided into pages that are, you know, part of that system. So so main memory is going to have sort of, you know, this setup where bits and pieces of this are going to come from process 1, bits and pieces are going to come from process 2. So, you know, we have a little page there, a couple pages here, a page there, so on and so forth. But the point sort of being that the processes themselves think that they own all of this memory. They are sort of unaware, blissfully unaware, that their memory is being sort of put into pages in this physical memory. The OS and the hardware just kind of handle that for them. So process 1 can access from address 0 to address OXFFFFFFF, right? Whatever our min and max addresses are. Process 2 can also access from address 0 up to address OXFFFFFFF. They can both do that. They can both request all of that memory from the operating system, and the operating system will just sort of under the covers map that into the actual physical memory in page size blocks. So I should maybe make these like all the same size, but, you know, together, so that we have, you know, these page size blocks that these systems are actually being allocated in the underlying hardware, but they get all of these little pages of space in actual main memory, rather than having these huge chunks that we would have had with contiguous allocation. So contiguous allocation, we would have had, you know, we would have had one big block for each process. Whereas here, we can have these interleaved in any way possible. We can sort of, put them in memory as needed. And each process to the programmer just thinks that they're getting all of memory, essentially here. They're not aware that they are getting sort of divided up into these little chunks of memory that they're actually being given. So is that a little bit more helpful here, hopefully, in terms of how this is actually working?
Yes.
Okay, cool. And that is a huge diagram now that I'm going to move down to here. So the sort of main advantage is that like the programmer doesn't have to be aware of memory allocation being performed by the OS. They can assume they own all of memory. And the OS just sort of handles that for them. Programmer don't have to be aware. That doesn't seem right. Oh, programmers don't have to be aware. Okay, sure. Fine, Google. I do have I added on sharing with comments. So as you're reading the notes and looking at them, if there are things that you feel like should be rephrased or things like that, or if I spelled something wrong here or there, you're welcome to make comments on it and request changes. I'm happy to sort of continue to improve these notes for future people taking this course if you see something that you want to have fixed up. So okay, so hopefully this is a better view of like how this is actually working, that each process kind of assumes it owns all of memory. Paging breaks that up in actual physical memory and gets it assigned to processes as needed. So we're going to move on then, unless are there questions, further questions on this? Okay, cool. So we're going to move on and talk about how this gets implemented in hardware. So we talked about page faults, the fact that when we don't have a page in memory, so like the first time we allocate each of these red pages, the first time that process touches that red page, we're going to have a page fault to initialize the virtual memory, find a physical frame that we can put it into, and initialize this mapping from like the red block in process 2 to the actual block in main memory. We need to maintain this mapping from page number to frame number. So we have this frame number and page number that we're going to switch. We have the page offset that stays the same, but each time we look at something from our process, like when process 1 accesses memory here, it's going to access it with an address that is a page number plus a page offset. And we go to main memory, we're going to have a frame number plus a page offset, which is what we're actually going to pull it from memory as. So there are a few ways that we can handle this. In most cases, what happens is we have a software page table that has some hardware support that goes along with it. So whenever we have a page fault, we access memory based on some virtual address, so some address that is local to process 1 or process 2. We are going to do a page table, what we call a walk. So a page table walk looks through the page table. In the case that the page table is just a bunch of page numbers and page offsets, it looks at all of the page numbers, it finds the right page number, and then it goes from the page number to the frame number. So the page table is like set up like this. So we have a per process table that just has page number to frame number mappings. We find the page number in that table, and then we return the resulting frame number. So the software can do this, and it basically just looks through this big table, finds the correct frame number, and then moves on. So what do we think some advantages and disadvantages are to implementing this in software? So what do you think an advantage of having it in software is? Or a disadvantage if you had one, Rupam?
I was going to say disadvantage is just more overhead for the CPU.
Disadvantage is overhead?
For the CPU, yeah.
Yeah, so I mean, software is slow compared to hardware. So if we are implementing it in software, that means we're going to have some overhead, especially if we have to do this lookup every time we access something in memory. So if we have to go to software every time we perform a load or store, and we have to look through a table to find the translation from virtual to physical address, that's going to be incredibly slow, right? This is, you know, a O of n lookup on a table, or at best, if we have it sorted, like an O of log n to search for something. It's going to be really a lot of overhead if we try to look at this. What about advantages? Like, what's an advantage to doing this in software? This may be a hard question. So
Does it
so good.
does it free up more like physical memory?
It frees up more hardware space for
Mhm.
sure. So yeah, it would free up physical memory. We can be a little, you know, it's a little easier to fit it. So we don't have dedicated hardware. Because as with most things, I mean, if we wanted to, we could implement everything in hardware, never do anything in software. It's just complicated and difficult. You know, all of you who just took 262, if you think about implementing a table lookup like this in hardware, it would be pretty difficult, especially if we're doing this, you know, for more complicated systems. So, I guess the better question to ask is does this allow us to be more flexible?
Yes.
Yes.
Yeah, right. So if we can implement different types of page tables, right? I could implement, you know, some sort of hash map. You know, I could change how the lookup happens. I can change the layout of my page table if I want to, which we'll get to the data structure behind it, or some of the different options for data structures, and you'll see that, you know, there's a benefit to being flexible here. Tyler, do you have something? I saw Mike unmute a bit. Okay, so it's more flexible because we can, you know, design our software to do anything we want. We don't have this built into the hardware. So you know, depending on the application, there may be advantages to changing how this implementation works. So the alternative to a software page table is to store the entire thing in hardware. So we can have a set of registers that has this, you know, we could basically have a page to frame register. I'm just going to steal one of these from up here. So we could have a page number to frame number registers. Give them a slightly different color. So we could have, you know, some set of these if we really wanted to. You know, n of them, basically to, you know, indicate that we have, you know, some set of page table entries, and, you know, we could have, you know, maybe like 64 entries or something like that. You know, however many we want to maintain. So we could have registers that look like this, that we have, you know, basically the page number and the frame number in each of those registers. This requires some amount of hardware space, right? Depending on how big our page numbers and frame numbers are. So this is probably like somewhat reasonable for a 32-bit system where we have 12-bit page numbers possibly, or 20-bit page numbers and frame numbers. If we get into a 64-bit system, then this is using, you know, number of bits times 2 times the number of registers that we have to fit all of this. So this can get pretty big pretty fast. And what do we know about the size of memory versus its speed?
As it gets bigger, the speed decreases.
Yeah, right. So as it gets bigger, the speed decreases. So if we want this to be fast, we want a limited number of bits for the page and frame numbers, and we want a limited number of registers, which is going to limit how many mappings we can have. So if we want the full thing, here we would need 2 to the 12th registers. 2 to the 12th registers, because we want to have every page number to frame number mapping here, which is a lot of registers. It's going to be pretty large at that point, a pretty large hardware structure. And we want 12 bits, or 12 bits times 2, so 24 bits per register that we're storing. And then we have to make these correct for the process that's currently running. So we could store these as part of the PCB, the process control block, and then swap them in each time a context switch occurs. But now we're looking at, changing out 4,000 entries in this register file, loading those from the process control block every time a context switch occurs, which would be very slow. Context switches are already expensive. If we tried to do this, it would probably be even more expensive. So this is just going to be a little too expensive to do it this way. And what we end up doing is sort of the best of both worlds. So we end up using what's called a translation look-aside buffer, or TLB. So you'll hear this abbreviated as TLB pretty much all the time, because translation look-aside buffer is a long mouthful of a phrase. So the TLB is a small cache that stores the page number to frame number mappings. So it's the same thing as what we would have had in registers, but it is a cache instead of a direct or like an actual structure that we have to have it be correct all the time. There are 2 ways to handle the fact that we might have different processes represented in this cache. So we can either have ACIDs, which are address space identifiers. These are essentially process IDs, so that this allows us to say which address space this corresponds to. Most of the time it's just a process ID is the same as the ACID, or the ASID. There are cases where we want to share memory between processes, and if we share memory between processes, we can end up with a situation where the page number in 2 different processes maps to the same frame number, which is how they can share, right? Because if we have them go to the same physical place in memory, they're reading the same actual bits from DRAM, and that's how they actually share memory between processes. So we use ASIDs instead of PIDs directly, because we might want to share these between processes. We can either have those as a sort of tag for the TLB, so whenever we look up a page number to see what the frame number is, we also check to make sure the ASID that we're looking for is correct. If we don't have that, then every time we context switch, we just flush the state from this this cache. So we clear everything out. In this case, we wouldn't have the ASIDs, we would just have page numbers and frame numbers, but then we clear out these 64 to 128 entries each time. So this is roughly what the structure is on like an Intel i7. They have this TLB that is 64 entries for the data TLB. So if we're looking for data in memory, it gets stored there. They have 128 entry TLB for code. So any code addresses that it's looking at go in a slightly different TLB. Mostly because those have slightly different properties. Like code, we tend to look up in the same chunks of things, but we have a lot of libraries that we reference. So it's a little more likely that we're going to be referencing very different pages in memory, and that we might be sharing a lot more things in code if we're looking at library code. And then the data TLB is a little smaller because 64 entries times 4 kilobytes is still a good bit of memory to keep track of. That's probably, you basically want this to be enough to cover the caches, so that if we are accessing things in a cache in the hardware, in the actual data cache, we want to make sure that the TLB is big enough that we don't have to have a miss in the TLB. So if we're missing the page number, frame number translation in the TLB, that means we need to do a page table walk and find it. We don't want to have a miss in the TLB when we have a hit in the actual cache. So we want them to be roughly the same size so that the same amount of memory is covered by the TLB as is covered by the caches. And it is what is called four-way set associative, which I'm not going to go too deep into here, but that essentially means that we can have like 4 things that map to the same place in the cache. So right below this, you can see this diagram where we have the page number and the frame number. And actually this should be, this should be page number and page offset in this diagram. So we split an address into the page number and the page offset. When we put that page number to frame number in this cache, the cache is essentially a big array that's indexed from 0 to number of entries. So if we have 64 entries, we have indexes 0 to 63. So number of entries minus 1, just because we're addressing like we do normal arrays. To find where it goes in the cache, we look at the bottom bits of the page number. So we just essentially, take that address. If we have OX 1, 2, 3, 4, 5, 6, maybe like A, B, B, C, C, D, D. The page offset, if we're using like half of it, would be the back half of that address. The page number would be the front half of that address. Split these in half, and then the page index, if we're using some number of bits, might be the 2 middle parts of that address. So basically, part of the page number, based on the number of bits we're using, will become the index into the cache. And we'll just basically pull those bits out and use that to index into this TLB to find the page number to frame number mapping. And then once we find that, we'll replace this whole part with whatever, the frame number is for that address. So we'll sort of substitute those in that way. Okay, so I'm going to split you up again for the next couple questions. So this is essentially just, again, math on pages. Actually, though, first, sorry, I shouldn't get ahead of myself here. I almost forgot about Kahoot. So let me load up the Kahoot for today. This is just a little bit of practice before we get into these questions with the just page table stuff by itself. So just trying to get you to look at the math behind the page table entries. There should be a pin on the screen now. I'll post it in case you're having issues. Also, is anyone having issues with the live stream today, or is it working okay?
I am having issues with the live stream, so I'm just going to take the L on this Kahoot.
Okay.
Or, yeah. Just been looking at the Google Doc.
Okay. I think I might have us try then Friday. I hate to keep changing how we're doing stuff, but I do want to find like the best way to do this that actually works for everyone. So I might try doing Hangouts with Discord in the background for the breakout rooms. If that sounds reasonable, then you can try this for voice, and then like the main lecture will be over Hangouts, because that seems to work pretty well for the video. But then I do want to keep having you work in small groups to answer questions, because that seems to work well to get everyone talking and participating. So I think maybe what we'll do is just have that work that way. Either that, or we can try switching to Zoom. Zoom has like breakout rooms that I'm not exactly sure how they work, but might fit the same bill. So maybe we'll try that as well. Sort of up to your preferences as well. So let me know if you have a particular preference there. We're missing one here, I think, still. Who are we missing? Okay, and I'll make sure I post this afterwards. It is recording, so I can post the live stream so you can check things that you missed. Sorry that it's having issues still. Okay, we're gonna get started then. There's a couple questions. They're gonna require you to do a little bit of math. So in a 32-bit system with 64 kilobyte pages, what is the page number for address OX12345678? The answers are the first half, the second half, or first half, the middle part, the last half, and then green is this is way too fast. Okay, nice. So most of you got it. So page number is going to be the first half of that address. So we're looking at, I tried to make these not too bad. So 64 kilobytes pages means 65536 pages total, which means we have 2 to the 16th pages. So that means we're essentially going to divide the address into two 16-bit fields, and that means that the page number is going to be the top 16 bits, which just happens to be 1, 2, 3, 4. Okay, nice job with the quick answer there. Next up, in a 32-bit system with 256 byte pages, what's the page offset for address 0, 1, 1, 2, 3, 4, 5, 6, 7, 8? And the answers are just in order from top left to bottom right. 2 bits at a time, or 2 bytes at a time. 1 byte at a time, sorry. Okay, that one's a little tougher then. So again, we're working with 32 bits. 256 byte pages should be 2 to the 8th entries. So we should have 8 bits that we're using for the page offset, and then the rest of those will be the page numbers, which means that given that our page offset is the back half of the address, we're going to end up using that OX78 as our page offset. So the page offset is like the index into the page itself, so the bytes that we're trying to access. The page number is the part of physical memory that we're trying to get to. You got jumped there. Nice work to the two of you that got that. Which page size requires the smallest number of bits to store the page number? And the answers are 4 kilobytes, 8 kilobytes, 2 megabytes, and 1 gigabyte. Okay, another tricky one. So smallest number of bits to store the page number. So the page number is the top part of the address. So that's this part here. The page offset is the bottom part of the address. So the page number gets smaller as the page offset gets larger. The page offset gets larger as there are bigger pages, since the page offset is the index into the page memory. So 1 gigabyte would be 2 to the 30th in terms of the page offset. So 30 bits there. Okay, we'll be close at the end here. Last up, true or false, it would be reasonable to have 1 gigabyte huge pages in a 32-bit system. Okay, so false. A 1 gigabyte huge page would be how much of memory in a 32-bit system? Another question, how much total memory is available in a 32-bit system?
Be like a quarter of the memory, right?
Yeah, it would be a quarter of memory because we have 4 gigabytes total. So we probably don't want to allocate a quarter of memory to a single page in this system. So nice. Okay, so final podium with 3 out of 4. Nice work, Rupam. Nice work, Ethan. And at the top, got Phil. Nice work, guys.
Yeah, Gary Kasparov, chess champion.
Good job to our runners-up as well. So, okay, just wanted to check in on that real quick. So that's not too bad, but let's get a little bit more practice here. Oh, sorry, we are out of time for today. We will start off with a little more practice on Friday. I just realized we just hit 120, so we'll start there. There is a reading for Friday, so make sure you do that reading quiz. Otherwise, I will see you then. And I'm going to send out, I didn't get to talk about the redone project. So the process scheduling project, just to keep you for another second, is going to be a short report in lieu of being